Today we are going to do section 5.3, the Fundamental Theorem of Calculus. It is on page 549, but before that, I want to first remind you of some of the theorems we already had that will be needed in this section. First, so please take a look, okay? These are just screenshots that I captured from your book. So, and first one is when you integrate something from let's see, from A to B, okay? And if A to B was to flip it around, then it's the same as putting a negative sign in front of it. That's the first one. All right? And the second one is that if you integrate from A to B, that's the same as integrating from A to C, somewhere in between, and then from C to B, right? And that is true even if C is outside A or B. Doesn't matter where C is. This rule applies. Now the next one I want to mention, remind you, is the intermediate value theorem, which says if f is continuous and stuff, right? And then if c is any number between a and b, f of a and f of b, then there exists a number c such that f of c equals to the z number. That is, you pick any number between the function of f, then you can find an x value called c that satisfied f of c equals to z. That's the intermediate value theorem. Next, let's look at the extreme value theorem. That's 4 points in. That's in chapter 4, which says if f is continuous function over some closed bounded interval, etc., then there is a point at which f has an absolute maximum. So you can find a big, which is called the big M, right? We usually call the absolute maximum the big M. And then there's similarly another little m where f has the absolute minimum. That's the that would be the extreme value theorem, which says the function f is you will be able to find at least one point where it's maximum and one point where it's minimum. And then the next rule, theorem 5.2, the comparison theorem, which we learned, I believe, just wherever we learned that, okay, in this chapter in a previous section, which says that if you have such a maximum minimum, the little m and big M, such that f of x is between little m and big M, in this theorem, it doesn't even have to be the absolute maximum or minimum, just whatever number the f of x is in between. One's smaller, one's bigger, right? Then the f of x, the integral of f of x is bigger than little m times b minus a and less than big M times b minus a. That's the comparison theorem. Next, we will look at theorem 4.7, corollary 2. Corollary 2 says we have used, where did it go? I'm not seeing it. Oh, yeah, it's right here. Anyway, corollary 2 just says that if f and g have the same derivative the entire time for every single x in the interval that we're interested in, then f is only different from g by a constant. That is, f equal to g plus some constant. Any constant, really. So that's the corollary 2 which we've had, and that's about it. That should be enough for us to go on with proving the fundamental theorem of calculus. And so let's look at page 549. Now that you have been reminded of all the various stuff we're going to need from the past. And let's look at theorem 5.3, the mean value theorem for integrals, which says that if f is continuous over some interval, and it's been continuous this whole time, very important, okay? If it's not continuous, our stuff can blow up in our face, especially if f goes to infinity within the interval, then you totally got a mess in there. and if you, and the thing won't work. The theorems might not work at all, okay? So f is continuous over the closed interval, then there exists at least one point c between somewhere within the interval, such that f of c f of c equals to 1 over b minus a integral of from a to b of f of x dx. Now this thing here is defined as the average, okay, at one point. So in other words, if you have a integral, if you have a function, then there exists at least one point where the value of the function is the same as the average, okay, which is fairly intuitive, but we're going to prove it. To prove, look below there. Since f is continuous, I'll turn my Kindle around. Okay, since f is continuous, first we're going to do the extreme value theorem, which we mentioned a little while ago, which is f has a maximum and a minimum. Okay, where so f is maximum f at some point, we will call it the big M. Okay, and then minimum f, we'll call it the little m. It will have those values such that for all the x in our interval from a to b, this statement is true. F is between the big F and little f. Next, we're going to quote the comparison theorem. By the comparison theorem, then, now let's remember what the comparison theorem is. Find it. Okay, the comparison theorem says if this is true, okay, look at it again, that means the integral of f is between the small m times b minus a and less than big M b minus a. So I'll write that down. By the comparison theorem, which we learned at theorem 5.2, that is maybe a section ago. So this equation holds. That is, the integral of f from a to b is bigger than or equal to small m b minus a, and then bigger but less than the big M b minus a. That is the comparison theorem. Okay, so far so good. Next page, we get and then we'll divide it, okay, by b minus a across the board. So then we get m less than or equal to dividing b minus a here times integral ab f of x dx, and then big M. See, I divided b minus a across the board, and then and next, this is, so what is that? That is some value. Okay, it is a value. We'll call it, oh, I don't know, c, maybe c, something. And let's not call it c. C might be confusing. We'll call it a. Okay, a for average, big A. A for average. Or, by the way, I'm referring to this entire thing. Okay. All right, because that's the average as defined at some other point. Anyway, so a for average. So now we are going to go back to the intermediate value theorem. The intermediate value theorem says if you have a function that is in between, where the function is between, the value is between 2 points, right? The f of, then there exists a function c, there exists a point c such that f of c, so there exists a point c such that f of c equals to a. Now, again, to repeat the intermediate value theorem, which I will remind you that is, if the function reaches two values, big M and fm and small m. See, the max f is here and the minimum f is here. That means you can find a number c such that it equals to whatever number that's in between big M and little m. And that's the intermediate value theorem. And at this point, then we actually finished proving whatever it is that we're starting to prove, which is, what was this? Which is the mean value theorem for integrals. Okay, so then so there exists a point which equals to this average here. and that is the end of the proof. All right, so let's look at example 5.15, which is quite straightforward. So I will assign that as homework, which just says that let's go find the value of the intermediate theorem. Okay, and yeah, so your function is just a straight line, and you are going to use the area of the triangle, find the integral, divide by b minus a, and you got it. That's very straightforward. Next, let's find the point where the function takes on its average value. Again, very straightforward. You you figure out what the value of the average value is, figure out what that is, and then set the function equal to that value, and then solve for x, right? Yeah, so again, very straightforward. So I will assign that as homework as well. Did I write it down here? Okay, give me a second. Next, we have come to the high point of this course, the Fundamental Theorem of Calculus. Very exciting. Now, what is the Fundamental Theorem? First, let's read it. This is on page 552. It says, if f is continuous over a closed interval ab, as always, then the function, and if the function is defined this way, let's look at the definition of the function. F of x is defined as the integral of a to the x f of t dt. All right. Now, then in that case, okay, these are all given. Now, if that is true, then the derivative of f of big F is equal to the little f of x. That is the fundamental theorem. Now, what that means, think about what that means for a second. First, let's figure out what this function says. What the big F says is defined as, for each x, you're going to plot the little f. Okay, here's a little f, and it started at a, and and here's b is over here, and x is in here somewhere, and to calculate f of x, for each x, you're gonna calculate the area under the curve of each x as x move along. Okay, so each x you gotta calculate the area. So, and that, which is a very odd function, right? But that we have probably never seen until now. But it's a function. That function is defined that way, and the point of the function is, anytime you need to calculate what x is, please do the Riemann sum of the area under the curve. Okay, and which is fine, but here's what's interesting. It says the derivative of such a function, if you were to define it that way, is equal to the little function itself. For some reason, that is, you plug the x back in here, and you're good. That's the derivative. And you think, and when you look at this, it's not obvious why that would be true. In fact, it shouldn't even be related. Why? Because the derivative of the function, the big F, is slope, right? At any given point, the slope is called the derivative. The small function is the area under the curve. How does the slope relate to the area under the curve? It doesn't, not normally, but in this case, it happens to be the same. Now, which is a very neat piece of luck, actually. So then, so that when you need to calculate the area under the curve, all you need to do is find the antiderivative. That is, find the object, if you can, whose derivative equal to this function. Then you're good. That's all. That is, you don't have to do the Riemann sum all the time, which means you slice it into thin slices, you add it up, oh boy. Whereas if you can find the antiderivative, then the whole thing is set. You just plug it in, and out it comes. Okay, so that is the meaning of the Fundamental Theorem of Calculus. What about the t? The t here is just the variable for the integration. Your book calls it a dummy. In other words, the t doesn't appear in the function itself. The t just tells you to integrate. Okay, you will integrate from the little f from a to x. In other words, this can be written. It doesn't have to be t. It can be written as any other variable like f of u or something du. Same deal. The point is, what does that mean? This means you're going to integrate. That is, calculate the area under the curve from a to x for each x that you need to figure out what the function is. So that's called the dummy. And yeah, so that's that. In case you wonder why are there two variables in the definition of a function that has only one variable, that is because that variable is to help you integrate or calculate the area under the curve. Okay, so having said that, let's prove the fundamental theorem of calculus. Okay, and to prove it, we are gonna go back to our good old definition of the derivative. So if you have a function, any function, its derivative is defined by our good old definition, which I will write it down. I'm on the next page. Limit as h approaches 0, f of x plus h minus f of x, okay, all over h. Okay, the good old definition for the derivative 101, right? Okay, and how are we going to get from there? Well, let's see. Now, so we are going to do, then next step, we're going to plug that thing into this definition and see what it looks like. And all right, so that requires quite a bit of writing. And so limit as h approaches 0. I'll write the h on the side because there's a big bunch of stuff here. The first f x plus h, by definition, equals to the integral goes from 0 to x plus h, f of t dt, right? Okay, we'll continue to use the dummy t, and minus just f of x, which is just that, and minus x plus h, sorry, just x, minus integral from, where did I say 0? I mean a, right? It goes from a. Yeah, from a to x, and then f of t dt. Okay, and then that equals to what? From a to x. Now we are going to flip this around to, that is, instead of a to x, we're going to flip it around and call it x to a. Now to flip things around, as the rule number, the top rule there, as you can see, if you flip stuff around, you have to put a negative sign in front. So that's what we're going to do. We'll rewrite this whole thing except for the negative sign. That equals the limit h approach 0 of 1 over h. Copy this whole thing down. A x plus h f of t dt, and then flip the sign and flip this. Okay, so it goes from x to a, and then ft dt. All right, so we did a lot of writing for that little bit. Now next, what we're going to do is apply a different rule. And what rule are we applying? You notice that these two things add up from x to a, and then from a to x plus h. Okay, a is sort of a middle point. And what does one of the rules we mentioned today say? Let me show you the rule again. The rule, okay, look at the second rule from the top. You see, the rule says if you have some point in between, right? And then if you are adding from a to c integral and then c to b, that's the same as adding from a to b. Okay, so we'll apply that rule, and that will equal, which reduces our writing a little bit. So the limit h approach 0, 1 over h, that doesn't change. Now we have only one integral left, big improvement, which goes from x to a to x plus h, or from x to x plus h, applying the rule that I just showed you. That's from, I copied it from the book, so it's in the book somewhere, okay? And then having done that, so we're doing pretty good. And we don't even need the parentheses. I will erase the parentheses because we only have one integral left. Ugh, that doesn't look that great. There. All right. So, and at this point, what is this? That is called the average. Okay, average of the, because you're going from x to x plus h, so the difference is h, and when you divide by 1 over h, that is called the average of the function. All right, and now we're gonna, well, we don't, that fact is not that interesting. What matters is this thing right here. We're gonna apply what we just proved, which is called the mean value theorem of integrals. That is 5.3, which is just a page ago. Okay, but I'll show it here. Wait for the camera to zoom in. Come on, my camera is supposed to be able to zoom in stuff fast, but it's not doing it. Okay, it's zoomed in. Now if f of there exists, so what does the mean value theorem for integrals that we just proved says? It says that if you have a function, then there exists a point between a and b such that f of c equals to the average of b minus a. Okay, all right. And so to apply that function, that theorem, we will have, in other words, this thing, just the inside though. So we'll write it down again. Just this thing, not counting the limit. Just this thing, okay? 1 over h, the stuff on the inside, 1 over h integral x plus h f of x. This is the average, which it will, by the mean value theorem for the integrals that we just proved, that equals to f of c, where c is somewhere inside from x to x plus h. All right, so that is, okay, so far so good. And then next, what we're going to say is that as h approaches 0, h is getting closer to 0, which means x plus h will approach x, which means c is going to approach x, okay? Because c is in between them, so as h disappears, then c is forced into x, sorry. C will approach x. And what does that mean? We have, which means that the limit as h approaches 0 of f of c will be f of x, because as h approaches 0, c approaches x, so it all goes there, and f is continuous. F has to be continuous for this to work. So then what does that mean? Then f prime of x, as we have gone over here, right, is the limit of f of c of this thing, because this thing equals fc. The f prime as x is the limit of f of c. We'll write it there here again as h approach 0 f of c, which is just f of x. And that's the end of the proof of the amazing fundamental theorem of calculus. And as you can see, we go, the main trick happens right here, where when you realize that as h approaches 0, f of c is approaching f of x. So then everything just comes out very nicely. See? So having done that, let's look at an example after I clean off the board. So the fundamental theorem of calculus says that if f of x is the integral of some function from a constant to x, then its derivative is the function itself. Okay. In other words, the integration and differentiation are sort of a reverse operation of each other. So, and now to look at a quick example, let's look at example 5.17, which we have g of x equal to something. Okay, and to slap on the fundamental theorem of calculus, they're asking you what is g prime of x. The g prime of x is simply you take the function inside the integral and change the variable to x, and that's it. That is the answer. See? And then it's a one-step quick answer for applying the fundamental theorem. Now, however, the next example is slightly more complicated. Let's look at example 5.18, which is, let me write it down. We're looking at example 5.18, which is on page 554. 554. Okay, now we're supposed to integrate something that looks a little weirder. Now what? Now to do that, let's recall what the chain rule is. The chain rule says if you have a function and it has some complications inside, okay, it's f of g. It isn't just a simple f of x. It's f of some other x thing in there, okay? And then you need to take the derivative of this whole deal. How do you do it? The chain rule states then you just take the derivative of the function as if it just have an x, and then when you're done, you plug g of x where x used to be, okay? And then you take the derivative of the g itself, okay? G prime, that becomes g prime of x, then you're done. That is the chain rule that we've been doing in the differentiation section. Now that chain rule, it doesn't change here, okay? So let's look at example 5.18, where big F equals to the integral from 0 to slight complication, square root of x, not just x, and sine t dt. Okay. All right. Now, how do what are we supposed to do? Find f prime of x. So f prime of x, we will apply the chain rule, which says normally first you take the derivative of big F, which by the fundamental theorem of calculus is just a little f. So we'll write down little f, sine of x, okay? And so that's the derivative. However, we can't just write down x because it's not x, it's the square root of x. So there's a complication. But we'll write that down anyway and then take the derivative of the complication according to the chain rule. Take the derivative of that, that's 1/2 square root of x, okay? And by the power rule, and then we are done. So see, the answer is sine square root of x over 2 square root of x. So that's it. And that's the example. Now next, let's look at example 5.19. Example 5.19, which 5.19, okay? It says we're going to do, now this one is even weirder, right? We are going to do f of x equals to, where you have a variable on both ends. Now, bottom end, top end, see there's an x there, another x there, and then t3 and stuff, dt. All right. Now what? Now, well, the fundamental theorem of calculus says down here it has to be a number, okay? It cannot have an x down here, but there's an x, so we got a slight problem. So what we do is pull off a rule from the past. The rule where it says, okay, look at the second rule again, which we used earlier, where it says if you integrate from a to b, the second one, it's the same as integrating from a to some other point, right? And then from that some other point back to b. Okay, so that's the rule we are going to apply. And that equals to, well, so that equals to f of x then equals to, we'll integrate from a to b. So we'll go from x to some other point. What do we call it? We'll call it 0. Doesn't matter what, really. It all works. But we'll pick a 0 because 0 is usually easier. So we'll pick a 0 dt, okay, and plus, and then the other one from 0 to 2x, t cubed, okay, dt. All right, now so far so good. Now this one we can use the fundamental theorem of calculus and then use the chain rule like we did in the previous example. But what about this? This is backwards. Now we need to flip it. upside down. Now, and then to flip it, remember the rule that we looked at today. Oops, this thing shrunk. Come on, get bigger. Okay. Now the first rule, which says that if you flip the numbers on the ends, on top and bottom, you just stick a negative sign. First rule. Okay. So we'll follow that rule. Apply that rule, and then we get, so this is negative from 0 to x t3 dt plus, that's just the same, that's not a problem, right? So that we will keep it that way, t3 dt. So now we're all good to apply the fundamental theorem of calculus, which says the first one is that you just write down what's in here. Okay, t3, you plug it with, replace t with x, and it's just x there, so everything's good. So f prime of x, taking the derivative by the fundamental theorem of calculus. The first one is just that, but the second one is similar. We'll also plug just the function itself with, however, we have to plug in 2x. Okay, the function is something raised to the power 3, but we have to plug in 2x, which means we have to apply the chain rule and take the derivative of this thing when it's not just x, which is just 2. And that is your answer. And that answer is, if you do some basic algebra, you get, that's, where's my negative sign? Don't forget the negative sign. It's right here. Okay, and then that you 2 to the third is 8. 16 minus 1 is 15. So the answer is 15x cubed. Okay? That will be the end of that example. All right. So let me clean off the board, and we'll go to next. So this finishes part 1, Fundamental Theorem of Calculus, part 1. For home, I'm going to divide this section into 2 parts so that everything is shorter, and so that you don't have. Well, anyway, so the problem, so please do the homework for just this part. And the homework I would like you to do is on page 562, problems 147, 49, 51, 53, 55, 57, 59, and 61. And when you are finished, please come back and I will talk about some of the problems. Now that you're done with the homework, I want to talk about some of the problems. First, problem number 153, which is the derivative going from 0 to square root of x, very similar to the example. What you do is, well, by the fundamental theorem of calculus, the derivative of the integral is just the function itself, and which in this case is just t, and you replace t with whatever variables on top, right? And then you have to take the derivative of what's on top, and that gives you some kind of answer. So that's problem 153. Next, 155 is similar in that the only difference is that there is a cosine, the cosine x, the function is, the x value or the function of x is on the bottom instead of on the top. So by that rule that I mentioned earlier, to make the fundamental theorem says that you have to, the x has to go on top. Okay, so you flip it around by adding a negative sign in there, and then now the x is on top. Then you apply the chain rule, write down the function itself except with the cosine x as the x, and then take the derivative of cosine, and then you come up with something. Now notice the answer is in the absolute value. The reason the absolute value is because if you don't, because the square root is defined only by absolute value. So if you remove the absolute value, then it's just sine squared. That wouldn't be true, because when you have absolute value sine of x times sine of x, sometimes if sine of x is negative, then this whole thing's negative. Whereas if you multiply it together, sine squared, that's always positive. That's why the answer is in this form. Okay, and then next, what are we doing next? I want to do problem 155. No, I did 155. Okay, next I want to talk about problem 157, where you see that is the you take the derivative of the integral. So as always, you that's just the function itself, except you stuff the x value in there as which in this case what's on top, the variable on top is not just x, it's x squared, but that doesn't matter. You replace t with x squared, okay, and then you have to take the derivative of x squared because it's not just x, and that gives you some kind of answer. And as always, because there's a square root here, see the x is square root, the answer has to be in absolute value form because square root is only positive. All right. Yeah, so that's that. And next, and the last problem I want to talk about is 159. I think I'll just copy that down out here, where 159 is problem 159, which says we need to take the derivative of the integral of goes from 1 to e to the power x. That's natural log u squared du. Now, whether this is u or t makes no difference because that's just a dummy, as your book says. Okay, and that's just a dummy for integration. And we apply the fundamental theorem of calculus, where it says you simply stuff whatever's up here in this function. So that will become natural log of e to the x squared. And that's the derivative. That's the derivative of the integral. And then at this point, we're done with calculus and going back to doing various natural log manipulations. I'm sorry. Being that this is e to the x, we're not done yet. We need to do the chain rule, which is take the derivative of e to the x. And the derivative of e to the x is, again, e to the x. So multiply all together. That's the answer, right? Don't forget to do the chain rule. Now, so having done that, now we'll just do some natural log manipulations. That thing equals to natural log of e to the 2x, okay? And then times e x squared. And everything in the power of the natural log goes in front. So that becomes 2x natural log of e and e to the power x. The natural log of e is 1, right? And therefore, this whole thing is just 2x e to the power x. And that's your answer. Okay, and that's the end of this part 1. And next we'll go do part 2 of the fundamental theorem of calculus.